Mandjes, and he asked me to say that he's done mathematics on 5 continents, including stints spent at Bell Labs and CWI. Today he's going to be talking about Markov modulated processing.
Well, Ilse, thank you very much. Can you hear me in the back?
Yes.
Yeah, everything fine. Well, let me first thank the organizers for inviting me. It's a real pleasure to be here and a great opportunity to present my work here. Let me start by telling how it all started. So this guy is Frank Bruggeman, and he's a colleague of mine at CWI, and he is into biomathematics. And he approached me with a very innocent question. So he asked me about the following model. He was interested in messenger RNA, and that is generated in his model according to a Poisson process. And each particle is served in parallel, so that sounds like an infinite server queue. So they stay in the system for a general amount of time, generally distributed amount of time. But there is a complication, and that complication is that there are, well, more busy periods and more quiet periods. So the source alternates between a high arrival rate and a low arrival rate. So that looks all pretty standard, and well, you recognize here a Markov modulated MG infinity queue. So the first thing you think is, well, everything in this field must have been done. And what I did was, well, I had a look in the book by Søren Asmussen, and I tried to look it up. But then it turned out that there was relatively little literature on this topic. For some reason, a lot of attention has been paid on Markov modulated single server queues, but not so much on Markov modulated infinite server queues. And well, it turned out, as I did some literature search, that there were maybe like 20 papers, and none of them had real nice explicit expressions for distributions or whatever. So that brought me to the following goal. I wanted to get some explicit results for this model, and the way I did it was that I wanted to look at time scaling. So what I'm going to do is impose time scalings on this model and try to get explicit results. So that is the common theme in this talk. I want to get, well, sort of explicit closed form expressions for the probability distribution in this model. Okay, so that brings me to the overview of my talk. I'm going to start with a model introduction, so I'm going to explain the components of the models that I'll discuss. That is not only infinite server queues, but also Markov modulated Ornstein and Uhlenbeck processes, and of course they are very much related. I'll show that in detail. Then I'll go to, well, let's say central limit type of results for the Markov modulated infinite server queue, and that is joint work with several people. So people from CWI, Joke Blom and Haldora Thorsdottir, Offer, who is not here anymore, Dave Anderson from the University of Wisconsin, one person of the group of Tom Kurtz, and Koen de Third from Ghent University. I do the same, but then in the large deviations regime. What can you say about tail probabilities? Then I move to, well, that's Ornstein and Uhlenbeck variant of the model, and I'll end up with something that is very related to the stuff that Peter Taylor talked about during his open problem presentation. So you have one background process that modulates several queues. And as Peter argued, in the sort of single server queue setting, that is hard, well, very hard to solve, but it turns out that in the infinite server queue setting, you can do a lot. And that is what I'm going to show. Okay, so let me start with the very basics. All of you will know this. An MM infinity queue, you go up with rate lambda, down with rate I mu when you are in state I. And of course, we know nearly everything about this model: steady state analysis, transient analysis, well, whatever you like. What is the complication? The complication is Markov modulation. So what do? You have a background process, x of t, lives on a finite state space 1 up to d, and it's an irreducible Markov process on that state space. So the transition rates are given by the matrix Q, and there is a unique invariant distribution pi. So that is how it works. So you have a vector lambda and a vector mu, and lambda I is the arrival rate when the background process is in state I, and mu I is the departure rate when the background process is in state I. So basically what you have then is this model. You go up with rate lambda xt. In other words, when xt is equal to j, you go up with lambda j, and then you go down with rate I times mu j. So that is the mechanics of the model. And of course, it's a very useful model also in communication networks, because basically what you have is that, well, users can alternate between different modes, and that's what you would like to model. Infinite server models can then be used as an approximation of many server models. Well, that's something we have been looking at in the past a lot. But as I argued before, it's also a useful model in biology. So this guy, Frank Bruggeman, convinced me that this is actually one of the relevant classes of models if you want to study problems of this type. Okay, as I mentioned, there's relatively little literature about this available. I write here less than 30. It's actually maybe less than 20. Perhaps I miss a full branch of literature, but as far as I could see, there is not so much known. And the results that are known are usually in sort of implicit terms. What do I mean with implicit? Well, you find results for, well, the transforms of MT in terms of their PGF, and that turns out to be a system of partial differential equations, or you get recursive schemes to find all moments. And those recursive schemes are still quite implicit, because what you have to do in every step is that a next moment can be computed from the previous by solving a non-homogeneous system of linear differential equations. So it's sort of, well, hidden behind all kinds of calculation procedures. And what I wanted to get is something that is more implicit, more explicit, and more insightful. The papers I'd like to mention are, in particular, the one by Osinite or Okinite or whatever you pronounce it, and Purdue. I don't know how to pronounce it actually. He comes with very clean results for this model, and one of the things that he sort of shows is that it's hardly possible, only in very special cases, to come up with explicit expressions for the probability distribution itself. Later on, there were other contributions by Kelson and Survey, that is like 1990. Adan and Frelix is like 2007, I believe. And Dauria is like 3 years ago. And that's actually a very nice paper that I will use later on. As I mentioned, for the Markov modulated single server queue, a lot is known. So think of the work by Newts and many other people. So if you do a literature search there, you will find, in the order of thousands of papers, including the ones about queues fed by Markov additive processes and that kind of thing. And the main finding is, for the Markov modulated single server queue, that you find a matrix geometric distribution. And that is nice, because that is a sort of generalization of the MM1, in which you see a normal geometric distribution. So that made people believe that there is something similar going on in the infinite server case, because there, in the single dimensional setting, you have a Poisson distribution, and well, then it would make sense that you would expect a matrix Poisson distribution for the Markov modulated variant. So that looked nice, but that turned out to be wrong. So that is not the case. And the question is, what can you say? What can you do instead? A remark: in the model that I just introduced, the mu i's depend on the current state of the background process. But you can think of another equally relevant model in which the surface times depend on the state of the Markov chain upon arrival. So that is what I call model 2. So model 1 is the one that I introduced. Model 2 is the one in which you sample the surface times upon arrival. And then there is a beautiful representation by Dauria, and when you think about it, it's actually quite logical. But suppose you start off empty, then it turns out that M of t has a Poisson distribution, but with a random parameter. And that random parameter actually makes sense, because, well, you enter with lambda I when xs is in state I, and then you have to stay in the system, right? That is basically what is written here. So this is a sort of logical representation for this model 2. So far about Markov modulated infinite server queues. Let me move now to Markov modulated Ornstein and Uhlenbeck queues. Well, these guys are Ornstein and Uhlenbeck. Till recently, I didn't know that they were actually Dutch. They worked together in Leiden. So in the 1930s, they worked together in Leiden, and they came up with their model. Actually, they were not the first to study that model, which was found out later on. Ornstein died in 1941 in Leiden. Uhlenbeck fled to the US. He lived in Madison, Wisconsin for a long time, and did great work afterwards.
Ornstein also worked with one of our Nobel laureates, Ornstein Zerning.
That's correct. So that is 1952. Zerning. That's correct. Zerning. Okay. So what did they study? Well, they studied basically this stochastic differential equation, and you see three parameters, alpha, gamma, and sigma. Sigma has to do with, let's say, the variance of the whole thing. Alpha over gamma is the sort of mean to which you revert, and gamma says something about the speed at which you do go to that stationary distribution. And what I wanted to tell here is that there is a striking similarity with the infinite server queue. Jobs are generated according to a Poisson process of rate lambda there, and they leave the system after an exponential amount of time. So you basically see the same dynamics as there. So there is an arrival rate which is not dependent on the current state, and you go down with a rate that is sort of proportional to your current state. And that makes it plausible that those models are very similar. That's something we probably all know, actually. And basically, there's a sort of folk theorem that I like to state, namely that everything that can be computed in explicit terms for MM infinity can be computed for Ornstein and Uhlenbeck as well. And that in many cases that turns out to be true. There are a few exceptions. It is very elementary to obtain the distribution of M of t in this model. If you do a bit of stochastic calculus, you see that the mean looks like this. So you sort of converge to alpha over gamma. I'm sure you've seen this before. And the variance can be computed as well. And there you get this thing. So for t to infinity, you go to sigma square over 2 gamma. Ornstein and Uhlenbeck is a Markovian Gaussian process and mean reverting. So that is sort of summarizing what is going on. So what is the Markov modulated variant of that? Well, basically, the alpha, the gamma, and the sigma depend on the state of the background process. So it's exactly the same as in the infinite server situation, but now in the Ornstein and Uhlenbeck setting. So you can come up with exactly the same description as what I saw before, what I showed before, but now locally the Ornstein and Uhlenbeck process has those parameters alpha I, gamma I, sigma I. So you get this stochastic differential equation. Here the state of the background process shows up. We call it Markov modulation. By the way, in the finance literature they call it regime switching, but that is exactly the same. If you do a bit of calculations, then you can actually prove the following result. Basically, the x, the position at time t, given that you know the trajectory of the background process, has a normal distribution with this mean and that variance. And that is interesting because that is very similar to what we found for the infinite server model. There we had a Poisson distribution with a random parameter. There we have a normal distribution. So this is a sort of example in which you see that they are very similar, these two models. Okay, let me continue with the first part of the talk, which is about central limit theorems. So what I want to do is to scale to impose some time scaling on the processes involved and to get a central limit theorem out. So what do? I look at a special case, namely I take the mu i's identical, and that means that model 1 and model 2 coincide. From that moment, model 1 and model 2 are the same. I do that because all formulas are simpler, but you can do that for the other models as well, for model 1 and model 2. But that is technically much harder. I just want to convey the main ideas, and well, if you want to go through these details, that is way tougher. It's quite trivial to compute the mean and the variance of the position at time t. So the mean position at time t amounts to computing the expected value of that, that Poisson random variable that I was discussing earlier. And basically, when you do that, and if you assume that the background process starts off in equilibrium, then you get this expression, this closed form expression for the mean value. And that makes sense, actually. When t goes to infinity, you see something that is quite plausible, the inner product of the pi and the lambda divided by mu, some sort of effective arrival rate divided by mu. You can actually also compute the variance in closed form, and that takes a bit more effort, but it's not hard. You can use the law of total variance. You condition on the path of the modulating process. You get this decomposition. The first part, because of the Poisson nature of the underlying random variable, is the same as this expected value, and you get this expression again. But the second part is the tougher one. You have to manipulate a little bit with these expressions. You again use that representation by Dauria, and if you go through everything, then you will recognize a double integral. You write this covariance as the covariance of indicator functions. Covariance of indicator functions are probabilities. So if you do all the bookkeeping correctly, you end up with this horrible expression, but it is closed form. And that there is something interesting here. So in this expression that you see here, you see the difference between transient probabilities and stationary probabilities integrated. And that reminds us of deviation matrices. So it's indeed true that deviation matrices play an enormous role in this analysis. And I'll show you how that works. The deviation matrix is defined in this way. I'm sure that all of you have seen this type of expressions. What you do is that you look at the difference of transient probabilities and steady state probabilities, and you integrate over time. And the ijth element of that matrix is given there. The next step is crucial in this talk. This is the time scaling that I'm going to look at. So what I'll do is that I'll scale the arrival rates linearly and the rates of the modulating process in a different fashion. Namely, I multiply them with n to the power f. So I speed up time there with n to the power f. And as you can imagine, it matters whether f is bigger or smaller than 1. If f is bigger than 1, of course, the background process moves faster. If f is smaller than 1, it moves slower. And that has crucial impacts on the outcomes. So if you do the calculations, I'm not going to do them because they're quite elementary and lengthy. But if you do it, then you get this expression for the variance. And that is quite interesting because what you see is two terms that both depend on n. This one linearly and that one like n to the power 2 minus f. And there you see that effect of the parameter f. You see a dichotomy, and that dichotomy says that if f is bigger than 1, the variance looks actually like the mean. And that makes sense, of course, because then the background process moves so fast that you effectively see a Poisson input, and, well, the parameter rho is given there. But the more interesting one is the one in which f is smaller than 1, so the background process moves slower than the arrivals, and then you get a variance that looks like this. So that led us to believe that there is something out there as a central limit theorem, and that central limit theorem has, well, the normal square root scaling if you're in the f bigger than 1 regime, and has a different scaling, 1 minus f over 2, in the other regime, f smaller than 1. And that is actually the thing we would like to show. So let me sketch the procedure. The procedure to come to a CLT is the following. I do that for the stationary situation. For the transient situation, it is a bit harder in terms of formulae, but the procedure is actually the same. It's a lot of bookkeeping, but it worked like this. So the first thing is that you set up a differential equation for the probability generating function of m of n. So that's a vector because it's jointly with the state of the modulating Markov process. Then you transform that into a differential equation for the moment generating function of your centered scaled process. So that gives you a system of differential equations there. Then the whole manipulation starts. So you play with that with deviation matrices and stuff. So that is the, let's say, the messy part that you have to find your way in. And then, if you do everything correctly, you obtain the desired Gaussian limit in which you see the dichotomy as I sketched. So that is the procedure that I would like to follow. Okay, so how does that work? Pkn is the vector of, well, the probability that you have k particles in the system and your background process is in state j. Well, then you transform with respect to z and you get this vector valued probability generating function. Then you set up the Kolmogorov equations and you multiply with z to the k, you sum, you play a little bit, and you get this expression, which is the generalization of the one for mm infinity. So here you have a diagonal matrix of the mu's and a diagonal matrix of the lambdas. Okay, so far so good. Then the next step is to manipulate this expression a little bit, and that we do by using deviation matrices and fundamental matrices. How does that work? So we define first the matrix capital pi, which is basically a d by d matrix with the equilibrium distribution in the rows. Then the fundamental matrix is the d plus pi. That is something, well, people have been working on a lot in the past. There are lots of standard properties for this d and f. I mentioned a few here. Q times f is f times q is pi minus I. F times 1 is 1. Y times d is d times pi is 0. And why is it that we could expect deviation matrices to show up in this analysis? Well, that is basically because of, well, statements of this type. So here you see something like the empirical distribution of, well, the state frequency of being in state I. Right? You subtract the mean, you scale in a way, and this turns out to converge to something of this type where you see the deviation matrix showing up here. So that is something that, well, that is sort of standard. You can, for instance, find it in a book by Asmussen. I came across something similar in an article by Kurt and Protter, actually a functional form of this. And this says actually why deviation matrices are likely to appear, right? So it says something about, well, the fraction of time that you spend in states. Okay. So what is the idea? We had that system of partial differential equations. We pre-multiply, post-multiply it with f, and we know that q times f is the identity minus pi, so that explains the first term, and then you get that second term. Well, then you have to believe me that when you translate that into a system of differential equations for the moment generating function of the centered and normalized process, that you get something like this. So this looks very messy. You see a z there, and that is defined in this way. And here you see the beta, and the beta has to do with that scaling in the central limit theorem. So you have to take the minimum of fm1. So this is something that, well, that turns out to appear. Well, basically then the next step is to tailor the z and to iterate the equation to get rid of all terms that are small compared to n to the power minus f. And then you end up with something like this. What do I mean by iterating? Every time that in the right-hand side here the p tilde appears, I replace it by the full right-hand side. And I keep on doing that until all the remainder terms are of this type. So I keep on iterating till I get this. Well, then there is a bit of matrix calculus going on. The goal that we have here is that we want to go from this vector valued moment generating function into a scalar valued. And basically what I do is that I add up all components. So I want to come to a differential equation for this object, and that is possible by multiplying the entire equation that I had by or one vector by n to the power f, and divide by theta, and you have to play a little bit with the expressions. You have to realize that one term is canceling, so that is basically the effect of the centering. And if you do everything correctly, then you end up with this differential equation. You have to use some identities that are not hard to verify. And this is nice, because what we did was that we reduced the whole problem to its essence. Because what do we see here? Well, what we see here is that it matters what the value of beta is. Remember, beta was the minimum of f in 1. And if f is smaller than 1, then the second one will cancel. If f is bigger than 1, the first one will cancel. So you really see the dichotomy expressed in a single formula. So here I draw that conclusion. Remember that beta is the minimum of f in 1. If f is smaller than 1, then only the first term in the right-hand side matters, and the second one vanishes. So you get a normal distribution with this variance. And if f is bigger than 1, the other one matters, and the first one can be neglected, and you get a normal distribution with this variance. So here you see really the effect of the two things, the effect on the variance of the Markov modulation and the effect on the variance of the stochasticity of the arrivals and departures. If f is 1, then both terms matter. So then the variance is actually the sum of the two. Well, the variance of this result for model 1 and model 2 can be written down. That's quite a bit of work, but it all works out. But also for the transient situations, not only for the stationary one. Previous work with offer covered just the case of f bigger than 1 and model 2, but by now we are capable of addressing all four regimes. It's possible to extend this to functional forms, functional versions, and that can be done by writing the number in the system as a difference between two Poisson processes with random time change. So that is basically the framework of, well, chemical reaction networks as worked on by Tom Kurtz. So we started that collaboration with Dave Anderson, and we basically got, well, the functional form, but that is something that we are currently working on. I'm sure you can prove that, by the way, in many other ways. So this is just one way to do it, I suppose. Also in that approach, which is completely different, you see that dichotomy showing up very nicely. So you really see at a certain stage where it matters that f is bigger or smaller than 1. So that is cool. Okay, that about central limit theorems. Let's move on to large deviations. I'll be pretty brief about that. What is the objective? The objective is to consider probabilities of this type. So you again have the same scaling, you scale your lambdas. So on average, the amount of stuff in the system also scales with n. And well, if you divide that by n, you get, well, a central limit theorem, as I showed, but you can also wonder, what is the probability that you are above level A? If f is bigger than 1, well, you get the same thing as what we saw before. Effectively, it's a Poisson input then, because your background process moves so fast. And basically what you see is that the large deviations coincide with the large deviations of a Poisson random variable with the appropriate rates. So that is quite easy. A similar thing can be done for the transient situation as well. So this is stationary, but for the transient, you can do exactly the same. You see crucially different behavior for f is smaller than 1. And we looked at the extreme case in that situation, namely the situation in which f is 0. So you don't scale the background process at all. And that means that your number in the system has a Poisson distribution with this parameter. And you want to know the large deviations of that. Well, what is the intuition in these situations? Well, basically that a single path of the background process causes you to exceed level NA. So the large deviations are fully determined by a single path. But of course, there is still the question, what is that path? And a first naive thought brought up by somebody who is here in the audience, actually, is to...
Doesn't want to be naive.
Exactly, exactly. So very good.
Not me, by the way. Naive to think.
Is that the background process stays all the time in the state that maximizes the lambda I over mu I. But that turns out to be wrong. It's almost correct, of course, but basically what you want to do is that you sort of maximize that Poisson parameter. So you may jump a few times, but you do that in a way such that this parameter is maximized. So on the optimal path, you may jump at most d minus 1 times, and the idea is that you sort of find the maximum expression for this thing. The interesting thing, by the way, is that you get a shape of the large deviation rate function that is a bit different from what you usually see. So usually you have a mean here, and the large deviation rate function looks like this. But in this model, you get something like this, where you stay 0 for a while and go up again. So that gives quite non-standard behavior, which is actually interesting. So we wrote a little note about it. So this remark I made. Okay, so that was what I wanted to say about infinite server queues. As I argued before, more or less the same can be said about Ornstein-Uhlenbeck processes. Many steps of the analysis that I showed you can actually be translated in terms of these processes. And let me go through them quickly. So this was the stochastic differential equation that we look at. So when xt is in state I, you have an Ornstein-Uhlenbeck process with parameters alpha I, gamma I, and sigma I. And exactly as was the case for the Markov modulated infinite server queue, you can come up with expressions for the moments. They can be found recursively, and again, they turn out to be non-homogeneous linear differential equations. But now it's a two-step recursion, actually, instead of a one-step recursion, and that has to do with the theta squared term showing up. An alternative to get these moments is to set up a system of partial differential equations. You can do that, and then everything is standard. You do the standard differentiation procedure, and then you will find relations for all moments. So there's nothing new there. Again, you can look at timescaling. This is essentially the same timescaling as the one that I proposed for Markov modulated infinite server. So you scale the sigma square and the alpha. It turns out that a direct computation using the law of total variance is impossible unless your gamma i's are equal to gamma. And if you do so, then you get nice explicit expressions. With similar techniques as the one that I showed you, you can you can derive a central limit theorem for the finite dimensional distributions. And again, you start off, double F, from a PDE for the Laplace transform of M of t. Many things are the same, many things are different also, but something that is the same is that, again, the value of f plays a crucial role. If f is bigger than 1, you essentially see the time averaging principle for all the parameters. So specializing to the situation that all gammas are equal and taking t to infinity, you get this nice expression for the limiting variance. It roughly looks like a linear term again, plus something that scales with n to the power 2 minus f. And that is, of course, not surprising in the light of what we saw before. This was a special case of identical gammas, but for non-identical gammas, you get the same type of dichotomy. There's nothing different there. And, well, basically the same underlying principles as the ones that we saw before apply here. Again, you can derive a CLT, and I think it shouldn't be too hard to prove the weak convergence version of that. So that is something that we would like to do. Large deviations, again, two regimes. The first one is the one in which f is sped up. So you jump faster with your background process than the natural time scale of the Ornstein-Uhlenbeck processes. And then what turns out is that you essentially see a single normal OU process with these parameters. So here you see the result. So essentially you get these normal if you wish, large deviations. Well, very briefly how you prove that. It's actually a bit of a standard thing how to do that. The lower bound is essentially focusing on the dominant way it happens. So the dominant way it happens is that you split intervals into subintervals of a certain length, t over square root n, but you can take any power of n smaller than n itself. And within each interval, you consider the scenario that the background process is very close to the equilibrium distribution. And then you find a lower bound on the mean and an upper bound on the variance, which gives you a lower bound on the probability. And that will give you the right result after letting delta go to 0. The upper bound is also standard. Basically, what you do is that you have that most likely trajectory of being close to that equilibrium distribution pi, and all other scenarios should vanish. And that is basically done in the following way. You again split in a certain manner, and you have to use that there is some distance still between n and n to the power 1 plus epsilon in this case. And what you basically do is that you split the event under consideration into two events, one in which the distribution, the empirical distribution of the background process is close to pi, and one in which it's not. And that second term decays super exponentially, so you can deal with the first one only, and then it's a matter of, well, finding again bounds on the mean and variance, but now an upper bound on the mean and a lower bound on the variance, and then you let delta go to 0, and then you have your result. So this is a sort of standard procedure, I guess, and it works. The other regime is that you scale your alpha and your sigma square, but your Q is not scaled, like what I did for Markov modulated infinite server. And then again, the intuition is that a single path determines the asymptotics. But then there's something interesting going on. It's not easy to find that path. So basically what you have to do is to solve this variational problem. You have to find path F that minimizes this decay rate. So that gives the most likely way in which it happens. But if you remember the formulas for this mean and this variance, well, there was that e to the power minus integral of gamma in those expressions. So it's not so easy to see which path optimizes this expression. So far I haven't solved this problem, so I frankly don't know. Of course, the intuition is again that you are not going to jump often with that background process, but you never know. So the question here is which path optimizes the decay rates? Well, of course, you can come up with the standard questions here. One question could be, what are the exact asymptotics of rare events? Another one could be, what can you say in terms of efficient simulation algorithms to estimate this probability? And basically, what you have to realize then is that there are two sources of randomness, one in the background process and one of the individual Ornstein-Uhlenbeck processes. And the question then is, can we come up with a good change of measure there? And I really haven't thought about it, but one idea that could be interesting is that you basically sample the background process and then compute the probability, because that is something that you explicitly know given the background process that has that normal distribution. So perhaps there's something possible along those lines, I don't know. The last part of my talk is about that coupling idea that is similar to the one that Peter Taylor sketched the other day. Basically what happens is that you have a single modulating Markov chain that is sort of driving different processes, and that creates a dependence between those processes, and that is of course interesting. So the example that Peter gave was the traditional classical Markov fluid model. When your background process is in state I, the first Q grows at rate Ri and the second one at rate Si. And that creates some dependence between the Qs, and you would love to come up with the joint distribution of the buffer contents of both. Well, that turns out to be hard. But the surprising thing is that things do work out in an infinite server setting. You can come up with nice expressions for the joint distribution of the two Qs if you if you work with infinite servers. Basically what you get is this system of differential equations for the steady state distribution. So that was somewhat surprising, but in the end everything works out very nicely, and basically you can do something very similar for model 2. So this is for model 1, and for model 2 you can do something similar, although the state space of the process that you have to keep track of is a little bit bigger. Okay, coupled. The word coupled is, I mean that they are driven by the same background process. So exactly in the same way as the open problem stated by Peter. So you have a single
service rates depend
on the same x of t. Yeah. So like what I write here, so there is an R of I for the first queue and S of I for the second queue. Both are single server queues, or just single queues in isolation. But the dependence is created because they are fed by a common background process. So basically you can again come up with formulas for the moments. You get two-dimensional recursions instead of one-dimensional recursions. You can do time scalings again, so there's not so much new there. And basically the same can be done for Markov modulated Ornstein-Uhlenbeck, also driven by a common background process. I think it's a very relevant model because different components in your model react to the same, let's say, outer world. So that creates the correlation between the components. So there is some sort of own stochasticity in the processes themselves, but also some shared stochasticity because of the common background process. And I think that is something that can be applied quite intensively, because if you think of, for instance, interest rates, well, people claim they can be modeled as Ornstein-Uhlenbeck processes or Markov modulated Ornstein-Uhlenbeck processes. And then there is, well, you can think of two regimes, one in which the economy is bad and the other one in which it's good, and that is reflected in values of the alpha, gamma, and sigma. But if you look at two individual interest rates, they essentially react to the same state of the economy, right? So they become coupled in that way. And that is exactly what you want. So this is a way to create dependence between individual components. And I think it's a very nice way to think about it. Another example is this is also a way to correlate stock prices. So there is that whole Markovitch theory about exploiting negative correlations between individual stocks. And that is something that, well, this gives you a handle on. So it could actually support portfolio decisions. And of course, it's also applicable in the context of communication networks, right? There is that outer world, and all the users of a network are reacting to the same outer world. Okay, so let me conclude. One of the things I really want to stress is that I think there are quite a number of open problems here. One of the things I would like to say is that, in principle, you could Markov modulate any SDE that you like. I gave two examples, but in principle you can, well, do whatever you like. For instance, one of the models that is used quite heavily in finance industry is the Cox-Ingersoll-Ross model, and that is a component of the Heston model. And you can try to do the same things there. I'm not sure whether it's going to work out. Cox-Ingersoll-Ross model has not, well, it doesn't have normal marginals, but non-central chi-squared. But things will complicate a little bit, but I'm pretty optimistic about it. A second thing that I mentioned already is important sampling. Exact asymptotics. I only have logarithmic asymptotics, but you really want to say something about, well, the prefactor or the prefunction, if you wish. There is that variational problem associated with the large deviations for the slow time scale for MMOU. So that gave that quite nasty optimization problem. And another thing that I would like to stress is that we now look at the distribution at a given point in time. But another thing to look at is the distribution of the running maximum. And for the MM infinity and Ornstein-Uhlenbeck, there are things known, but one may wonder whether that could be extended to their Markov modulated versions. General conclusions, models that allow fairly explicit analysis. I hope I convince you about that. various asymptotic regimes can be explored. So I looked at several of them, but I suppose there are quite a number of other regimes that you could have a look at. And I think there's a lot of work that still needs to be done. Thank you.
Just a very general question. You mentioned that the problem started by contacting this biologist, and then you worked on all these classical questions from our point of view, which is great,
exactly.
but are they relevant to the question that...
Yeah, so that is a big debate. So he's the type of guy who sees models well, he discusses a lot with other biologists, and he makes models out of it, and then he publishes them in, well, the Journal of Theoretical Biology and that kind of thing. So, of course, it's questionable to what extent it's really practically useful. But, well, of course, there is some interaction going on now, and hopefully it's going to lead to something.
I mean, was the question, give me a good model for the things I'm doing, or give me an answer for the behavior of DNA? What kind
Biologists are usually of the last type, I think. They really want to have numbers, and they're already happy when you can, for instance, compute probabilities by just solving the linear equations that give you the steady state distribution. So his involvement was pretty limited.
Sure, but I'm just know nothing about biology, that's why I'm asking about there.
Neither do I.
I suspect that your low and high rate is just the activation of the gene. The gene is not always active, and when it's active, it can produce messengers. So I suspect that the model comes from this observation.
Okay.
And this is the way it is used. It's a three-step process where it describes generation of protein, in fact, in the end. And the messengers, mRNA, are generated by polymerase, and the gene must be active for that.
I see.
So you have some enzymes that block sometimes the gene.
I see.
So, and this is, I guess, the modulation is coming from this point.
Yeah, I see. Thanks.
So, back on the history of this before you got started, did I understand correctly that the Markov modulated infinite server, infinity, but Markov modulated, this Daria did solve for something?
Yeah, so what he did,
Stationary distribution?
um,
Or limit distribution?
he found fixed point equations that give the transform of the steady state amount in the system.
And this is the Poisson distribution with a random parameter.
Yeah, that is the observation that he keeps on using. Yeah. And the other thing he does is a recursion for all moments, but that is sort of following from that, just differentiation of that first thing, of that fixed point equation.
Right. And it would appear that something you never mentioned was this sort of classical argument on infinity that uses the order statistics property of the Poisson process. And this Poisson distribution with a random parameter is a manifestation of that same argument in this much more complicated context, right? Does Daria make that observation, use that approach?
Actually, his papers, I found it very hard to read. He comes with the right result in the end, but the way he comes to that result is, I find it hard to read. So that argument is
Why was his result, I sort of lost the track in there, not good enough for your purpose? What you want to do different or better is what? That you want to be time dependent, that distribution is too complicated, you want to get at it another way?
Well, the Poisson distribution with random parameters, so there's still stochasticity there. You want to have something for the distribution.
You have to evaluate that distribution.
Exactly, and that depends on the entire path of the Markov chain.
Agreed.
That is the whole thing.
I see. So it's that distribution. Basically, the problem's been solved up to a level,
Exactly.
and now you're sort of pulling apart that module.
Yeah, exactly.
Right, so let's thank Michel again.